Our first success criteria in our matter unit is to be able to explain the states of matter and its phase changes in terms of energy transfer and particle organization. But before we get started, let's remind ourselves what matter is. We learned that in our measurement unit that matter is anything that has mass and volume, which is why we learned how to measure those things in our lab. But now we're going to be adding the following two criteria. So now there's a total of 4 criteria that represent matter. So in addition to having mass and volume, we also need to understand that matter is made up of particles. And particles are a generic term for atoms, molecules, or ions, all of which we're going to be studying in our next unit about atomic structure and theory. But the last criteria, in addition to matter having mass, volume, and made up of particles, is understanding that those particles are in constant motion, even in states that we think they are not moving. So we have 3 states of matter. We have solids, liquids, and gases. And for this particular demonstration, we're going to assume that we have the same number of particles in each box. So when we have a solid, we can represent our solid as a cube within a cube. Because a solid has a fixed volume, meaning it has a defined amount of space. It has a fixed shape, which means that it has its own shape and it's not going to take the shape of the container. The solid also cannot be compressed, meaning we can't squeeze it into submission to fit another shape. We also need to talk about a solid in terms of the forces between the particles. The particles are attracted to each other by something called the strong force, and a solid is in a close packed arrangement. And these particles vibrate in fixed positions. So even though we believe that the molecules or particles in a solid are not moving, this is not true, as they are vibrating in position, and vibration indicates a movement. So imagine we're taking our solid, and we can assume that it's ice if you need a visual, and we let it sit out for a while and it turns to water. So now we've gone from a piece of ice that has a pretty distinct shape, and now this piece of ice is forming a puddle, whether that's in a glass or on the countertop. So a liquid has a fixed volume, meaning it has a defined amount of space it's going to take up, but now it does not have a fixed shape, and it will take the shape of its container, because now the molecules or particles are farther apart and are sliding against each other and can move around a little bit more freely. A liquid still cannot be compressed. Even though it takes the shape of its container, its fixed volume means we can't compress it into submission. Because it's a liquid, we can compare the forces between particles in terms of being weaker or stronger, and because the molecules are a little further apart, we can assume that the forces between the particles are weaker than that of in solids. So not only do these particles vibrate in place, just like in a solid, but they can also now rotate and then translate, which means move around. So say we leave that piece of ice out for a really long time, and all of a sudden it's gone. But it didn't just disappear, it's turned into a gas. And we can diagram a gas by filling up the container that it's in. So a gas has no fixed volume, and it has no fixed shape, and it takes the shape of its container. So a similarity between a gas and a liquid is that they both take the shape of the container, but the gas does not have a defined volume or amount of space it can take up. Gases can be compressed. So if you're familiar with aerosol cans or spray paint, all of that gas is compressed into a small area, which allows it to flow out of the straw. So because there's no fixed volume, we can assume that the forces between the particles are taken as zero, meaning that there's no attractive force between the particles. And just like in a liquid, but perhaps a little bit faster, particles are still vibrating, rotating, and translating, but they're being moved at a faster rate than in the liquid. So as we go from a solid, liquid to a gas, that all relates to the kinetic molecular theory. And per IB, the kinetic molecular theory is the theory that explains the physical properties of matter. So what they mean are the three states of matter, and then the changes of state, and these represent the phase changes. In terms of the movement, and when they talk about the movement, what they're talking about is the actual movement of the particles, so particle speed. And then and the arrangement of its constituent particles. So when we talk about the arrangement, we're talking about the actual arrangement of the particles, and that's pretty self-explanatory. So arrangement or placement of particles. But IB typically has pretty standard and professional terminology. So let's break this down even farther in a student-friendly language. So we've already done some of that by saying that the physical properties of matter represent the states of matter, and that the changes of state represent the phase changes in terms of its movement, so the particle speed, and the arrangement or the placement of particles. But how we can word it is as we increase the temperature of a piece of matter, we are increasing the energy of the particles, causing the particles to move faster. And because they're moving faster, that means we're increasing the kinetic energy, which is the energy of motion. And as the particles, or as the matter, speeds up, they will collide more, And that actually relates to the collision theory, which we'll go over when we talk about reaction rates in our chemical reactions unit. The particles, as they collide more, will spread apart. Because the forces are getting weaker. And the states of matter will change. And something that's important to remember is that the opposite, which in this case is cooling matter or making things colder, is also true. So even though that's a particularly long-winded explanation, that is a more student-friendly way to think about the kinetic molecular theory. So now we're going to turn the page of our note sheet and talk about those phase changes. So a phase change is a physical change, and we're going to learn about physical and chemical changes later in this unit. And these are changes that occur when matter transitions from one state to another. So it's easier to think about it in terms of a triangle, where we have our solids, our liquids, and our gases. So we're going to move around the triangle first in a clockwise fashion. So we're first going to go from a solid to a liquid. So the direction is solid to liquid. And this phase change is called melting. And in order to go from a packed type of particle to a more free-flowing particle, we're going to have to increase the energy of the system. And the reason we're going to have to increase the energy of the system is that we need the molecules to spread apart, so we need to increase the energy by adding heat. Now we're going to go from solid to gas. Oh, by solid, I mean liquid to gas, I'm sorry. So to go from liquid to gas, that process is called vaporization. But the process of, say, boiling water is called evaporation. But IB calls it vaporization, and it's important to know the difference in terminology. And in order to go from liquid to gas, we'll need to increase the energy of the system because we want the particles to even go even farther. And so in order to do that, they need to move faster. We're going to keep going in this direction around the triangle. So in order to go from a gas to a solid. So now we're going from a state of matter that's really far apart to something that the molecules are more packed together. So in this case, in order to go from a gas to a solid, we're actually going to have to decrease the amount of energy and lower the temperature of the system. And this phase change is called deposition. Now we're going to go backwards, or counterclockwise. So we're going to talk about how to go from a solid to a gas. So we have a packed state of matter going to a more free-flowing. So in order to go from a solid to a gas, we're going to increase the temperature of the system because we're skipping a liquid state. And this is called sublimation. If you ever played with a fog machine, you usually get dry ice, which is solid CO2, and it completely skips the liquid phase and goes right to a gas. The process of going from a gas to a liquid, This is called condensation. And in this case, we're going to be decreasing the amount of energy. We're slowing those molecules down. They're getting a little closer together. And so we are decreasing the energy of the system. And last but not least, in order to go from a liquid to a solid, we're going to be slowing those particles down even more. So we're decreasing the energy by decreasing the temperature. So to go from a liquid to a solid, this is called freezing. So I would bet that you've heard of melting, vaporization, condensation, and freezing, but we're unaware that solids and gases have a direct pathway. So if these two are new for you, make sure to make a star or an exclamation point next to them so you remember to study them in the future. Now, as in everything in science, we can make a visual model or a graph of what's happening. And we're going to come back to our states of matter diagram. So in this particular graph, we have temperature on the y-axis and the energy input on the x. So think of your energy input, especially because this is water, as like putting a pan of ice over the stovetop. So we're adding heat. Temperature and heat are not the same thing. Temperature is a measure of the heat, and heat is the actual property. Very important to know the difference. So if we start with ice, remember that ice is a solid and it has a fixed shape and a fixed volume. And it's just kind of hanging out there. And what this line is telling me right here, this line in particular, is that the solid, in this case the ice, because we're talking about water, will stay in this state until the temperature reaches 0 degrees Celsius. Then when we get to 0 degrees Celsius, so at 0 degrees Celsius, melting and freezing occur at the same time, which is kind of crazy to think about. So this section right here at 0 degrees, melting and freezing are happening at the same time. And to know which direction we're going in, we have to take the context of the graph. So because I'm inputting energy, that means I'm adding energy, I know that I'm focusing more on the melting portion of it versus the freezing portion. So in order to go from one state of matter to another, when we're talking about energy input, we need to remember that as we go from one state to another, we're going to be adding energy in the form of heat. So we're going to be, so make an arrow and say adding heat, which means we're increasing the temperature, which means we're increasing the kinetic energy. So if we take our solid ice and we add heat to right above 0 degrees Celsius, that means we're going to have a puddle of water. So this line right here represents the liquid state. And what this line tells me is that the liquid water will stay in this state from 0 degrees Celsius to 100 degrees Celsius, because 100, sorry, I covered it up before, is right here. Then once we reach 100 degrees Celsius, so at 100 degrees Celsius, evaporation and condensation simultaneously happen at the or occur at the same time. But once we go over 100 degrees Celsius, then we have steam, which is the gaseous phase. And remember that the gaseous phase will take up the entire container, whether that's a small box or a room. So when we have a gas, it'll stay at this state. So it'll stay in the gaseous state from 100 degrees Celsius and up. And remember that the opposite is true. So if we take away energy, then we can go backwards along this graph. So the next time I see you in class, we'll be focusing more on the states of matter and phase changes and the kinetic molecular theory, and combining it with things that we already see in an everyday life.